Okay, well, when we last left our hero, we were in the middle of doing the proof. And so let me kind of catch up a little bit. Let me kind of pick up where we left off. What we had was for D1 was as small as possible. And that set S. I remember what S was. S was the collection of all integers such that there is a basis where you could represent something in A in terms of these integers in that basis. And D1 among all throughout all S, D1 was the smallest positive integer that we found in there. Right, and so where we left it had concluded last time that doing a little prestidigitation and using the fact that D1 was the smallest integer, we actually had D1, X1, where X1 was defined to be Y1. Plus Q2 Y2. So what we had done last time is we had rewritten each of these KIs in terms of the Euclidean algorithm under division by D. We had reworked everything. We called X this thing that we got, and we had concluded that D was D1 X1. And that's where we left off. And so what we have now is a basis for F. This is by the previous limit that we had last time. And I'm gonna pull out a little bit here. I'm gonna let the small one here, H, be I'm gonna let H be the subgroup generated by these elements Y2 through Yn. Now, of course, this is part of the basis. So Y2 through Yn is a linearly independent set. And so what they span is, of course, going to be a free abelian subgroup of F. And notice that F is X1 direct sum H. The reason that X1 and H span this is because this is a basis, right? So notice that this direct sum here contains X1 and it contains all these Y's. So since this is a basis of F, you got everything, right? And the direct sum part, what you need for the direct part is the intersection of these two is 0. And that's true because, again, this is a basis, right? So if you have something, if R X1 is equal to, let's say R1, it's R2, Y2. If there's an element in the intersection of these two, it can be written in this form as well as this form, correct? And this implies that R1 equals R2 equals in 0 because of the fact that this is a basis. These must be linearly independent, and so the intersection is 0. So that's why this is a direct sum. Okay, and the claim that we're going to make now is this abelian subgroup that we're looking at, and I claim has this particular basis, is what we were calling A. I'm going to claim A is the direct sum A intersect H. I want to make that wild claim here. And so to this end, as before, V, which intersect A intersect H, is again 0. Right? The proof is pretty much the same as last time. And the question is, the real big question is why does that, why do V and A intersect H, why do they span all of A? And so to that end, let's let U equal T1 X1 So let's pick U. Now, since U is in A, it's certainly in W. And so I can write U as a linear combination of the of X1 and the Y's. And so I have to really show that it's a linear combination of V and the appropriate Y's. And so to this end, let's write T1. This is kind of repetition here. So once again, I'm going to take whatever this coefficient of X1 is, and I'm going to divide it by D1, give me a quotient of Q1 and some remainder that has to be smaller than D. And so A contains U minus Q1B, right? Right, so what I've done is I've replaced this with D1 Q1 plus R1. Now the D1 times the X1 is V, right? And so this is really Q1V that I'm going to bring over here, and there'll be a little bit more of this left over. So this is R1, X1 plus Q1, wow, 2, I'm sorry, Q2 by 2. Okay. So I took my D1 and I hooked it up with X1 making a V. So I sucked this over here. Now U is in A by assumption, and V is in A as well. So this difference right here is in A. And so but this means R1 is in X, because R1 is a coefficient, X1 up to Y2 up to YN is basis for F. And so this, by definition of S, this is an element of S. because it's an integer multiplied with basis on it, right? But D1 was minimal. So R1 is 0. So this thing is essentially gone. And so what this means is U minus Q1 P and this is in A intersect H. Because of course the left side is in A, and this is in H, because H is what's generated by the Y's. Therefore, I've got what I want, because an arbitrary U in A can now be expressed as something in B plus something generated by these things in A intersect H. Okay. All right. Any questions? So where are we at now after all this trouble? Well, let's point out that if A intersect H is 0, then A is singly generated by what if not? They intersect H is non-zero, then there exists a basis, which I will call X1 or X2 to Xn. Of H and positive integers D2, D3, and Dr. Such that A intersect H is free abelian. The basis D2, X2, D3, X3, Dr. So there's the inductive hypothesis for it, right? If A intersect H is about 0, then you get this free abelian. A intersect H is free abelian on this basis here. These all divide. And so the only thing left really, so since F is X1 and A is this, the only thing, well, so if this is the case, then X1 of Xn basis And we get the following basis for A. So the only thing left to do is we have the D2 divides D3, D3 divides D4, and so forth. The only missing piece of the puzzle is we need to show that D1 divides D2. Do that. So
I have a question just on the induction hypothesis
Sure.
part. So we're doing induction on the rank of the group or the set, right? So are we claiming that A intersect H has rank less than N? In that case, that will
Yes.
require these induction.
yeah, A intersect H has rank less than N.
Okay,
That's right.
and so why is that specifically?
We start at the index of 2, right? So,
Okay,
right, so
so
there,
it has to have less.
yeah, so it's rank less.
Okay, that makes sense.
So, my goodness, I beat this horse to death. So let's divide D2 by D1 again. And as you might guess, what we want to do is we want to show that the remainder is 0. So note that let's look at x plus q is a basis for f. So once again, this is using that previous lemma, right? Because really, we know that this is a basis, so I can add a multiple of x2 first one, and it's still a basis. And let me write this down carefully. D1 times x1 is q x2 plus R1 x2 is D1 x1. Oh, I don't know where that is from there. Well, what is this? This is dx1, d1x1. And this is d1q1 plus r1, which is d2. So if you look at that particular element, this is in A. But again, and so let me make it clear, R1 is an S. Again, we have a linear combination, so this means that R1 is in that special set S. But by minimality, R1 is equal to 0. Therefore, Any questions? Let me give you a quick corollary. I pointed this out actually pre-case, maybe last time, but this is worth noting. Corollary. Here it is. Let A be definitely generated. Abelian. Generated by n elements. So this is a notice I didn't say free, it's just any finitely generated Abelian group generated by n elements. Then any subgroup can be generated by less elements. And any subgroup H in A be generated. Let's see. This is kind of a cool theorem. So if I walk up to you on the street and I give you an abelian group that's generated by 20 elements, if you find any subgroup of that, it can be generated by 20 elements or maybe less. It's economical. This is wildly untrue if you remove, well, of course, it's silly if you remove the word finitely generated, but if you remove abelian, this is not true at all. You've got a homework exercise where you've got a two-generated group that has infinitely generated subgroups. Why is this true? Let me just sketch the proof for you. Short proof of this. So suppose A generated by x1. And let Fn be free. Let me be clear, free of abelian. So what we have is there exists a homomorphism right? This comes from our proof earlier that any abelian group is the homomorphic image of a free abelian group. And if our group that we're interested in is generated by n elements, it's a homomorphic image of a free abelian group on n elements. You can do it on n elements. Everybody okay with that? Now, what I'm curious about is a subgroup. So now suppose A notice that the inverse is a subgroup. Well, I'll call it something G. So this is the pre-image. So by phi inverse, of course, phi is not necessarily an invertible mass. What I do mean is, I mean this is the set of all the garbage in Fn that goes into G. I'm sorry, goes into H, the subgroup of A. Right? Notice that if A is in the pre-image, B is in the pre-image, that means both A and B go into H. And so A plus B has to go into H2 because B is a homomorphism, right? This is a subgroup. Notice that G is generated by, we call it G1, G2, with M no more than N. This is by the theorem we proved because G is a subgroup of a finitely generated free abelian group. And so G, I know that the theorem works for G because we just proved it. That is, it's generated by no more than N elements. It's subgroup free. Am I okay with that? And notice that B of G equals H. And so H generated by C G1. So there's a couple of details to check. Yes.
Never mind. You were just sketching out. What's that? How do you know that you don't get too much stuff? That's
Too much stuff where in H?
H, yeah.
Because of the fact that this is free image. So by definition, everything in G has to pop into H. Is that clear?
That's good.
Okay. So what we're going to do now is we're going to use this knowledge at hand to give the classification of all finitely generated abelian groups. This is cool because basically, if you want to understand group theory, of course, the non-abelian case is a lot harder. But one might think, well, we're sort of half done because if you give me any finitely generated abelian group, I can tell you what it looks like. We can write it down, we can classify it, we can just put it, it's like a zoo. We can put them all in cages and talk about exactly what they are. Abelian is important. Finitely generated is important. I can remember I did mostly ring theory, and I got off on a tangent doing some stuff with groups because I needed some group stuff to help what I was doing. It was my last year in graduate school. I needed to know some stuff about abelian groups. And I remember thinking, how hard can this be? Right? So I went to the library, checked out a book on abelian groups that do not assume that they're finitely generated. And oh my goodness, I mean, the author might as well have been Stephen King. It was awful, right? It was like The Shining. So these things can be very bad if you don't have finitely generated. So let me start off. Yeah, I'm going to talk about this later. So let me start this off here. I'm gonna sort of revisit this theorem. So I am going this theorem. And this tells you, I'm going to tell you a couple of ways to write this. How many of you have ever heard of elementary divisor decomposition or invariant factor decomposition? Maybe. I almost guarantee that you all have seen it, but maybe not in that name. But we'll tear this apart, and then I'll show you how to really kind of do things. Every abelian group is isomorphic to a finite direct sum of cyclic groups. Okay, already I'm kind of wowed by this theorem, right? Because what it says so far is any finitely generated Abelian group is a number of it's just some finite direct sum of copies of cyclic group. And lo and behold, I know what cyclic groups look like, right? They either look like Z or they look like Z mod N, right? So that's cool. But we can actually arrange these cyclic summons in a particular way. The finite cyclic sum then orders one into B, where one five into five. So let me give you all an example. I'm going to print this with what we have. I'm going to print this pretty short. Let me give you actually a numerical example, maybe to get everybody, I hope, on the same page. How many of you have ever seen? So suppose okay, there is one of my favorite video groups. I was dreaming about it last night. And you know what I said to myself? I would like to be able to write this in terms of a number of copies of cyclic groups in increasing order. Now, anybody know how we rewrite it in this form? Right? Certainly, this is a direct sum of cyclic groups. I think we can all agree. Cyclic group order 6, 24, 250, 686, 105, 525. Right? However, it's certainly not true that you have this. So let me take you through this a little bit. And let me know if this is or is not familiar. Okay, good. So what I can do is I'm going to write isomorphic now. 6 is 2 times 3, which results in 2 primes. So I can break up Z6 this way. Are you all familiar with that? This actually follows from one of our homework problems. You know how to break up Z24? That's what you do. You do the prime power. So right. So right, because 24 is 2 cubed times 3. So I can break it up into C prime power. Now, 250. That's 2 times 125, so it's 2 times 5 cubed. So I would break that up this way. $686 is 2 times 343. Power of 7. That's 7. 105 is, what is 105? It's 3 times 5 times 7. And finally, 525 is 5 times 105, and I've already done 105, so this is actually Z3 direct sum Z5. Okay, everybody cool with that? I want to make sure that we're all together now on the yellow brick road here. Any questions on how I broke that up? Now, there's two ways, well, there's not just two ways, but there are two common ways that people break this up. And if you like doing things with finite structures, both of these ways to break it up are important depending on what application you're working, like coding theory or whatever it happens to be. If you want to be able to count units, if you were doing, sometimes you like to break this up into prime powers, sometimes you like to break it up here, like very fast. So here's two ways you can do this. Way one, we call this the elementary divisor decomposition. And you know what it is? It ain't nothing but collecting prime powers. And I don't have to do this, but I'll collect highest powers. Let me start with 2. 2 doesn't appear here. There's no 2 here or here. There's a Z2, a Z2, a Z8, and a Z2. So I'm going to go Z8, Z2, 2, Z2. And this is, make sure I check these babies off. There we go. And that's the first bit. So this is basically everything, all the subgroups that have 2 to the power. Okay, let's go to the next prime, comes up 3. Let's see what I've got here. I've got a 3, a 3. Another 3, and another 3. So I got 4. Okay, we check those off my bucket list there. Next prime, looks like we got some 5s. Let's see. You guys are all dead here. Okay. I've got a 125, so I've got a 5 cubed, 5 to the first, 5 to the second. So I'll get 5 to 5, just organize myself later. And the last thing that I have is Z7 for the prime 7. And I think this will strike everything off. It looks like I've got a 7 to the 3rd power and then 2 to the 1st. This decomposition is isomorphic to this first mess that I had, this chaotic bit here. So of course you can put this back together and rewrite this way, but this is more organized because I've got it grouped by the primes. And like I said, sometimes that's a very convenient way to look at things. This is called the elementary divisor decomposition. Everybody okay on how we did this? Now I'm going to do the invariant factor. So I'm going to get it like this. This is shorter. I can start it over here. Basically, I'm going to do my m's in reverse order. it says in the theorem that we go from smallest to largest, M1 divides M2. I want to go from largest to smallest because it's easier for me to do. Because what you do, if you have the elementary divisor, to get the invariant factor, all you have to do is just be greedy, right? I want to hook this back up together into cyclic pieces, right? And what's the biggest cyclic piece that well, remember, I took these apart by prime powers, right? I can put them back together by prime powers too. And if I'm a greedy person, which I'm going to be, what's the biggest cyclic piece I can take? I've taken this piece, and this piece, and this piece, and this piece. Right? And so my first cyclic piece would be z to the, I'm not going to multiply this out, 2 cubed times 3 times 5 cubed times 7 cubed. Whatever that stupid number is, that is one giant cyclic piece of vector. Z mod, whatever this number is. Right? So that takes care of you, and you, and you, and you. And then you just tunnel down. What do we have here? We have a 2, a 3, 25, and a 7. Okay. So that's 150. So I guess that's 1050. Or I don't care. You could write it as 2 times 3 times 5 squared times 7. Let's see, I took all you off. Then I have Z2, Z3, let's get monotonous, Z5, so we're up to 30, Z7, so Z42. Let's see, 7s and 5s are dead, and I've got one more on here. I got Z6. So, in the theorem here, I would have M1 is 6, M2 is 42, M3 is 1050, and M4 is 2 cubed times, well, it's 210 cubed divided by 9, whatever that is. Very big.
Is 42 the same factor?
Yes. But see, we use it, did I do that right? Oh, I think I may have filled off on it. See, let me check this. 8, 3, 125, 343. The first one's good. Then 2, 3, 25, 7. And then the third one. So I think your point is I forgot a 5 here, didn't I?
Yeah.
Is that correct? Okay. I'm sorry about that. You're right. It should be, yeah, I don't know how this. Okay, any questions on it? Yes.
Also the case of the number of, I can't really remember, is it the number of ways that you can write a group as, so a group of this order as the sum of cyclic groups of prime order? Does that identify up to isomorphism, the number of groups of that order, or the number of abelian groups of that order?
This is just a number of abelian groups, right? I mean,
But if we're talking about the other direction.
oh my goodness. Yeah, I mean, so if you look at the order of this group, whatever it is, the order of this group will be the product of all these, right? So it'll right. The order of this group will be 2 to the 6 times 3 to the 4 times 5 to the 6 times 7 to the 5th. So if I look at all groups of that order, there's a lot of many groups. There's many more non-groups. Yeah, it's huge. But I don't know if I addressed your question.
I was saying, we can use this process to identify all of the, can we use this process or use this idea to identify all of the finite, or to identify the number of finitely generated Abelian groups up to isomorphism?
Yes, yes, so.
Because this
for
just
example-
implies that we can write one in this, but it's we get information the other direction as well. About this.
That is correct. So for example, I might ask. let's see, how many groups Abelian order 720 are there? And 720, I guess, is 6 factorial. So this is 2 to the 1, 4, 3 to the 2. So what you can do is you can ask yourself the disjoint questions: how many Abelian groups of order 16, how many of order 9, and how many of order 2? And by what we're doing here, how many groups of order 16 are there? And actually, the fact that the prime is 2 doesn't really matter that much. C16, there's one of them. And so that's just one block. After you break it up into 2 pieces, Z8 direct sum Z2, or you can go Z4 direct sum Z4. And that's it for 2 pieces. How many ways can you break it up into 3 pieces? I think that's it for 3 pieces. And how many ways can you break that into 4? Well, everybody. So it looks to me like there's 5 groups of order 16 that are Abelian. Everybody see how I did? And what about 9? Well, 9 and Z3. Some Z3, and you're done. And then 5 is prime, so that's it. Everybody okay with that? So, answer the question: how many groups of order 720 Abelian are there? Looks like there's 10, right? Because you've got 5 choices here, there's one of these 2 choices here, and you're stuck with this. So it looks like there's 10. Okay, any questions? Okay, let me just kind of outline the way the proof's going to work for this, and it's terribly easy given what we have. Prove part of it. Suppose A is generated by n elements. Then A is the homomorphic image of a free Abelian group on n elements. Let Fn be free Abelian. So there exists a feed from Fn into A, so on. Now, the kernel of feed is a subgroup of a free Abelian group on n elements. So we're gonna generate this, M1, X1, M2, X2, M2, X2, where X1, X2, Xn is the basis. Or, Fn. And now it's fairly easy to see that when you take, this is n copies of C divided by this, what you get is Z mod M1, Z mod M2, Z mod MP. These divide each other. And whatever's left over is just the directional number of copies of C. I'll clean up those details a little bit next time, but this is a good place to end. Any questions? Any questions? How about you all out there? Everything okay? All right. Listen, I hope this class and everything is going well for you all, the whole graduate experience and all that. I know it's a crazy time with the COVID and there's lots of stress going on. I want you all to consider me a resource. If anything comes up, find yourself getting behind in my class or any others, feel welcome to talk to me. So, anything else for now? All right, you all have a good one, and we will see you. Bye-bye.